As Kentucky NSF EPSCoR research pushes the boundaries of advanced manufacturing in the Commonwealth and beyond, it's vital that the materials used to create sensors and electronic components are flexible, cost-effective, and more sustainable. Dr. Kyle Schitzenbaumer, chemistry professor at Transylvania University in Lexington, Kentucky, is working on materials that do just that. His research centers on understanding the structure-property relationships of colloidal semiconductor nanocrystals. A recipient of one of Kentucky NSF EPSCoR's annual research awards, Dr. Schnitzenbaumer's project has two facets. One is committed to advancing nanocrystal research for the benefit of device engineering and manufacturing. The other is committed to enhancing the scientific literacy of the Lexington community.
Yeah, so nanocrystal is a very small piece of crystalline material. This is something that we trap on the nanoscale, so we're talking about crystals that are on the order of 1 to 10 nanometers in size, much thinner even than a human hair. Nanocrystals are sometimes referred to as artificial atoms. They can sometimes be viewed as kind of like atoms or the building blocks of materials. These nanocrystals have potential to be used as sort of building blocks of arrays of these nanomaterials. The goal of my research is to gather information about these materials and how we make them that can then be used by the engineers or the applied scientists that are actually going to go manufacture the devices. Once that work has been done and once that foundation has been laid, that allows other researchers to sort of streamline their efforts because they're not having to go in and characterize the things that they make to the same extent.
Nanocrystals are known to strongly absorb and emit light. For those reasons, nanocrystalline materials are attractive to applications like sensing, where one or the other needs to happen. Some of the applications for these materials come in the form of optoelectronic devices like monitor displays or solar energy harvesting devices.
Both of these devices are essentially operating on very similar principles. A television display is essentially something where you put electrical energy in and you have light being emitted from the material. And a solar cell is something where you have light energy coming in, you're looking to turn that into electrical energy. And so these nanocrystalline materials, being very strong light absorbers, are key candidate materials for use in manufacturing.
Schnitzenbaumer's team also looks at ways to create nanocrystals using environmentally friendly and sustainable practices.
The majority of work on nanocrystals has been done with toxic heavy metal containing materials like lead and cadmium. Those are experiments and materials that have led us to understand a whole lot about what kinds of things we do synthetically that influence the ultimate properties of these nanocrystalline structures or these heterostructures. For actually taking and using these materials in consumer devices, though, we're going to be looking at targeting things that are not as toxic and a little bit more environmentally friendly. And we're going to want things that can be synthesized economically. If we can make a material that has desirable properties in a cost-effective and environmentally friendly way, we have a material that has a high likelihood of being used in manufacturing settings.
Dr. Schnitzenbaumer's team can observe the size and properties of nanocrystals based on the color and intensity of light they absorb and emit.
As the crystals themselves grow, the surface chemistry, which we can control synthetically, is something that allows us to not only keep that crystal on the nanoscale, but also allows us to tune how quickly the crystal grows. And if you're looking for a particular size, you can arrest that growth, sort of creating all the crystallites in your sample of a similar size. Smaller crystals are going to have a higher energy gap, and so those are things that are going to do absorbing or emitting more on the blue edge of the spectrum. The crystals that you allow to grow longer will grow a little bit larger, and those are crystals then that are going to sort of absorb or emit more on the redder edge of the spectrum. And this is the operating principle behind some of the optoelectronic displays, like a television display, where you want different colors. You want a red, you want a green, you want a blue. That can be achieved by using different sizes of these nanocrystalline materials.
2 Kentucky NSF EPSCoR funded spectrometers will assist his group in studying these properties.
We're using the funds from EPSCoR to purchase 2 pieces of instrumentation. The first piece of instrumentation is a miniature absorption spectrometer, which we can use inside of our air-free glove box, where we can work with our materials. We can measure them all while avoiding any oxidative effects, which may influence the ultimate properties of the material. The second is a benchtop fluorimeter. What that does is allows us to measure quantitatively the fluorescence, the light being emitted from our samples as a function of the energy that we excite them at, as a function of the synthetic choices we make when we make them, morphology, surface chemistry. We'll even have the capability to make our different emission measurements as a function of temperature of the material, which will allow us to sort of investigate some of the underlying structural properties that lead to resulting material.
The second facet of Dr. Schitzenbaumer's project involves connecting art and science in public spaces. With the goal of benefiting scientific literacy, the group will use spectrometers to capture optical spectra and generate accompanying audio to create an experiential art installation. Schnitzenbaumer believes interdisciplinary collaboration like this is vital for solving complex problems in our world. At a liberal arts institution like Transylvania, this collaboration is celebrated.
We're particularly well positioned for projects like this, where we're trying to incorporate input from some different disciplines, and sometimes disciplines that are often viewed as being very different from each other. But that's one of the hallmarks of how we approach things, and I think that's how we as a society will actually be able to address the challenges of the future, is taking interdisciplinary approaches. One of the ways that we can reach the public is by sort of taking science into public spaces, spaces that members of the public already visit. If your everyday life takes you into an art gallery, then I think that we should have some opportunities for people to interact with scientific ideas in a digestible way for them. One of the things I'd like to do is take some of the spectroscopic techniques that we use to study our materials that we synthesize and sort of port those over and incorporate them in something of an interactive exhibit, where people could see visually the color of something. And as a spectroscopist, what we do is we take and we use a spectrometer to sort of measure the intensity and the colors of light that this material absorbs or emits. And with that digital data, we could then take that data and translate that into an audio signal, so that people could sort of have some auditory component where they can sort of hear a representation of the data generated by a particular material. And so that's one of the reasons that we are hoping to take some of these scientific ideas and bring them into a space where people are typically walking in expecting to interact with some artistic elements.